Before we start talking about mutually exclusive events, we need to make a small review of what we call the general rule of probability. The general rule of probability means that if I want to determine the probability of A or B, I need to determine first the probability of A, the probability of B, add them, and then check if I have an intersection, and if the intersection exists, then this value will be subtracted from all the expression. So, to understand in a better way this general rule for probability, we're going to use this example in here. They tell me that we have a sample space that is formed by the numbers from 1 to 9. Let set A be the numbers 1, 2, 4, and 7, and set B, let it be 1, 2, 3, 5, and 9. So what we're going to do is determine these values. Now, as you can see, we have certain elements that are coincident in both sets, and we also have a group of values that are not part of the sets. So let's make a Venn diagram to identify that situation and to have a very clear idea of what is going to happen with the probabilities that we're going to analyze. So I'm going to put set A, I'm going to create set B, and then we're going to see what happens. Now, in set A, let's remember that we have the elements 1, 2, 4, and 7. And in set B, we have elements 1, 2, 3, 5, and 9. And as you can see, 1 and 2 is common in both of them. Therefore, 1 and 2 is the intersection of the two sets. Then we start writing 4 and 7, and then we write 3, 5, and 9 as part of element B. But in here also we need to consider the values of 6 and 8, which do not belong to A and B, but they belong to the sample space. That means that we can write 6 in here and we can write 8 over here, indicating that they belong to the universe or sample space, but they don't belong to the two sets. Now let's start analyzing the probability. Probability of A will be all the possible sets, all the possible elements in set A divided by the sample space. So in other words, I have 4 elements that belong to set A, and these are going to be divided by the sample space of this universe that we have in here, which is equal to 9. This is already a fraction in simplest form, so we leave it like that. Then, let's find the probability for set B. The probability of B will be equal to all the elements that are part of set B, which is 5 elements, divided by the universe that we have in this set in here. So, it will be 5 over 9. Again, we check this fraction, but in this case it is already in simplest form. Now we proceed to do the other probabilities, the intersection and the union. To see the intersection, now that we have the figure, and it's very easy to identify it with the figure, we just look at how many elements are part of this area. So, P intersection A and B will be equal to the number of elements that I have in here, which is 2, divided by the sample space that we have in this set, that is 9. Again, the fraction is written in simplest form. We don't need to consider simplifying. The final answer, the probability between A union B, will be equal to probability of A, applying the rule, plus the probability of B, minus the intersection of them if this intersection exists, which in this particular case we have a value. So now we start replacing the problem. P of A is equal to 4 9s. P of B is equal to 5 9s. And to this addition, we're going to subtract the value that corresponds to the intersection. So 2 over 9, and as you can see, since we have the same denominator, we just add them and subtract. 4 plus 5 will be 9, and 9 minus 2 will be equal to 7 over 9, and this is a fraction in simplest form. There we have the probability of A union B. I hope that this Venn diagram helped you with to get the idea of the problem. This is the general idea on how to apply the general rule for probability. Now let's see another example. Example number 2 takes us to another situation. Here we have the following problem. On one bag, we have 6 blue marbles, 4 green marbles, and 8 red marbles. What is the probability of picking a red or a blue marble from that bag? So if we analyze the possible situations that we have in here, is that we have a number of marbles that are inside one bag. In this case, the sample space, right, will be equal to the addition of all the marbles that we have in here. In this case, 18. So now we need to analyze what is going to happen if we pick a red marble or if we pick a blue marble. In here, we are talking now about mutually exclusive events, because it is impossible that you pick up a marble that is going to be red and blue. According to the situation, we only have blue, green, or red, but not combinations of them. Therefore, the probability of finding an intersection will be equal to the empty space. And that empty space tells me that I'm going to cancel out this part of the equation of probability, and I'm only going to work with the addition of the two probabilities that I have in here. So, the probability of picking a red marble will be equal to 8 over 18. And in this case, people, we have to simplify our fractions. So we can see that this can be simplified by 2, both of them. So we will have 4 over 9. So we write it in simplest form. Then we're going to have the probability of picking a blue marble. So probability of having a blue marble, that will be 6 out of 18. And if we simplify this fraction, we're going to have 1/3, right? Or 1 over 3. Now that I have the two elements in here, well, it's very easy to apply the formula, because now the probability of picking red or blue will be equal to the probability of red plus the probability of picking a blue marble. So in this case, we're going to have 4 over 9 plus 1/3. And if you simplify that expression, you're going to have as an answer, well, look for the common denominator between 9 and 3. Okay, then you do the combinations and you apply the process, and finally the answer will be 7 over 9. And in here we have the probability of a mutually exclusive event in which you cannot have a situation in which there is an intersection. The intersection between red and blue doesn't exist, so we only operate the part that is the addition of the two probabilities. And this is what we are going to call the probability of picking a red or a blue marble. We'll continue with the next example, in which we are going to use combinations to determine the probability. Example number 3 implies the use of combinations in the process of finding the probabilities. And apart from the process of combinations, we're going always to use our rule of probability that we have in here. Now, Here we have a different situation. It says that from a group of 14 boys and 12 girls, 4 students must be selected for the student council of the school. What is the probability that at least 2 students are going to be boys? Now, they tell me that at least 2 students are going to be boys. So this tells me that I can have different situations in here. One of the situations can be the following: that we are going to have two boys and 2 girls. Another possible situation can be 3 boys, 1 girl. And a final situation can be, can be considered, is 4 boys and none girls chosen. Okay? So, based on those, these are going to be the events that we can have in here, and if you see, they are all independent, one from each other, so they will be ruled by the concept of mutually exclusive. But first of all, let's define the sample space of this problem. The sample space indicates me that if I am going to choose 4 students from this bunch of students that I have in here, I'm going to have 26, because it's the addition of 14 and 12, combination 4, with the formula being 26 factorial, 4 and 26, 4 factorial, sorry, 26 minus 4 factorial. So the final answer in here will be the value of 14,950. This is going to be my denominator in all the possible cases. So what do we mean by possible cases? Okay, let's analyze one by one. What will be the combination in here? Or how do I get this combination? This combination will be 2 boys and 2 girls. The 2 boys, they go from here. So 14 combination 2 multiplied by 12 combination 2. And this will be divided by 26 combination 4, which we already had from a previous step. So when you apply the process, you will end up having 91 times 66, all this divided by 14,950, and as a final answer, you will have the simplest form of this expression, which is 231 divided by 575. Remember always to write your final answer as a simplest form. Okay? Now that we discovered the first probability, let's analyze what happens when we have 3 boys and 1 girl chosen. So the combination will go like this: 14 combination 3 multiplied by 12 combination 1, which will be the combination to obtain 1 girl, divided by 26 combination 4. With this, what we obtain is the following situation: 364 multiplied by 12, and this divided by 14,950. With this answer written in simplest form, we're going to have 168 divided by 575. And here we have the second probability. Now let's finish up this one. We have the last element, which is going to be 14 combination 4. That means the 4 of them are boys. Times 12 combination 0. That means choosing none of the girls. And this divided by the sample space, which is 26 combination 4. So in here, we end up having the situation 1,001 times 1 divided by 14,950. So in here, we're going to have the expression 77 over 1,150. Now that I have the three probabilities in here, what corresponds is I add them using the general rule. So in this case, we're going to have P, A, if you want to call this event A, union B, union C. So in this case, we're going to have the addition of the three fractions that we have in here, 231 over 575 plus 168 divided by 575, and finally 77 divided by 1,150. And when you simplify all this expression, what you end up having is 35 out of 46. And this will be your probability that at least 2 boys will be selected for a student council from this set of students that we have in here. Hope that you understood the process. Remember, this is the part in which we apply combinations. So you have to be very careful with the combination formula. Don't forget these 2 elements always in the denominator. And then you only proceed to simplify your expressions. Thank you very much.